Good afternoon, welcome to Calculus. Here's a statement of the mean value theorem, which is used to prove the fundamental theorem of calculus. The mean value theorem states that if f is continuous on the closed interval a to b, and so far, it starts out just like the intermediate value theorem. So, the intermediate value theorem starts out if the function is continuous on the closed interval a to b. So far, no difference. And differentiable on the open interval a to b. So this blank is differentiable on the open interval a to b. Then there is at least one, this should be lowercase c, there's at least one c in the open interval a to b. Such that f prime of c, that is the slope of the tangent line, is equal to the slope of the secant line. So, speed it up a little bit. Much better. So this is an expression you're about to see that slope of the secant line is f of b minus f of a over b minus a. This may seem like a set of random math symbols swimming on your paper. It's like, what is the concept here? Well, verbal, graphical, algebraic, numeric technology, and real-world based understandings. I mean, if all I give you is the algebraic understanding of the mean value theorem, then that's rough. But if we bring in the graphic understanding to say that the slope of the tangent line is equal to the slope of the secant line, that's a little bit better. But how about a real-world understanding of the mean value theorem? Okay. Before we fill in this stuff down here, let's look at a real-world understanding of the mean value theorem in a way that impacts your emotions. You ready to get emotionally engaged in calculus? Yeah? Okay, then let's take a trip to Grandma's house for Thanksgiving. Now, the plan is to leave at 9 a.m., but we're not leaving till 1 p.m. Why is that? Well, we were delayed. Your brother didn't get home from soccer practice until noon. So your brother got home late. And to make it even worse, you promised to bring Grandma a pumpkin pie for Thanksgiving. But Mom doesn't have the pie done. It's still baking in the oven. Finally, 1 o'clock, the family's ready to go. We're at the point, 1 p.m., we're at the 50-mile mark. You actually happen to live on Interstate 94. Your front yard backs up to the mile marker 50 on Interstate 94. Grandma happens to also live on Interstate 94 at mile marker 400 over in Michigan. Guess the apple doesn't fall that far from the tree. So you both happen to live on the same road, just 350 miles apart. Your goal is to be, you promised Grandma that you'd be at her house at 3 p.m. Okay? So, check this out. Here's the story. You hop in the car. Your velocity is 0. You start moving. It's like, boy, we don't want to be late. And speeding up, foot on the pedal, speeding up, and then all of a sudden you hear a scream from the front seat. Oh no, I left the pumpkin pie in the oven. It said, take the foot off the pedal, stop, turn around. You're going the wrong way. No, we actually went through the median. We're going the right way. Going back home, get the pumpkin pie. Okay, now we're really late. Things were looking sketchy at first, but now we're back home. Run in, get the pumpkin pie. Now, pedal to the metal. Now we're really moving. And, oh, there's red flashing lights in the rear view mirror. Oh, no, speeding. So we have to come to a stop again, stop for a while the police officer gives us much needed correction. Thank you, officer, I needed to be confronted because I was lacking self-control as I was trying to make my way, weaving through all the other traffic on Interstate 94. So now we figure the best thing to do, because we have to be to Grandma's house on time. The ends justify the means here in this Machiavellian sense here. No, actually, so we figure, well, the only way we cannot get caught is if we exceed the speed of light, so that the officer's radar gun will not, the radiation coming from the radar gun will not be able to catch up to our car. The problem is that you can't even see the sign because the light doesn't bounce off the sign that says it's time to exit now and go into Grandma's house. So you end up overshooting Grandma's house, come back. Okay, so finally we make it. What the mean value theorem says is that there's at least one value C on the interval 1 to 3, such that the slope of the tangent line is equal to the slope of the secant line. Let's color code this a little bit. What could be more emotional than Grandma and getting stopped by the police? Police officers, a lot of emotion. Grandma, lots of emotion. We've got them both in the same problem. So, what's the slope of the secant line? The slope of the secant line is the slope of the line that passes through 1, 50 and the point 3, 4. There it is, right there. The slope of the secant line in green, that's going to be, we'll call it f of b minus f of a over b minus a. Once again, we're talking about f of b minus f of a divided by b minus a comes out to f of 3 minus f of 1 over 3 minus 1. F of 3 is 400 miles. F of 1 is 50 miles. So it's 400 minus 50. 400 minus 50. You went 350 miles in 2 hours. We're talking you averaged 175 miles per hour. Now, based on the mean value theorem, 175, the mean value theorem can give an officer of the law a basis for giving you a speeding ticket, even though she's never there pointing the radar gun at you. She doesn't have to be there pointing the radar gun at you. All she has to do is use the mean value theorem, and she can give you a ticket because of the truth of calculus. You see, suppose there was a timestamp. I mean, suppose I-94 was a tollway where you have to, do you remember going on family trips where you get a ticket to get on to the turnpikes? So the Pennsylvania Turnpike, you get a ticket to get on, and it's time-stamped location, so time and mile marker. And then you get a time-stamped ticket when you get off of the turnpike. Well, they can do the same thing with Easy Pass and iPass. They can tell where you are, what time you're at a given mile marker, and where you are. Suppose you live at an iPass. Not only do you live on I-94, you live right there at an iPass station. You just have to imagine that I-94 is a tollway, even though it's not, but just imagine it is. And that Grandma lives at an iPass also, at the 400 mile marker. So, based on those two values alone, those two timestamps, they know your average speed was 175 miles per hour. The mean value theorem says there's at least one value, C, such that the slope of the tangent line, I'm going to put my tangent lines in blue, the f prime of C, that your instantaneous rate of change is going to be equal to your average speed. your instantaneous speed is going to be equal to your average speed at least once. And you can eyeball this. Look at this. You can see there's actually 6 times when your actual speed was equal to the average speed. Like, for example, as you were speeding up, right when you left the house, the slope of the tangent line was equal to 175 miles per hour. And then mom screams, "I left the pie in the oven." So now you take your foot off the gas, you're slowing down. As you were slowing down to 0, there was another point. So here's the first C, C1, when you were speeding up. Mom screams. Second C, you're slowing down. You passed 175 miles on the way down. Then you get back home, and then, I don't know if you surpassed 175, but you probably did. 175 miles per hour on the way up. Police is in pursuit. Police are in pursuit. You slow down. Now you're down to 0. And then you're speeding up again. So there are actually 6 values, 6 times. C3, C4, C5, and C6. There are 6 times at which your slope of the tangent line was 175. The mean value theorem guarantees there will be at least one. So suppose your story is not as interesting as the trip to Grandma's house. Suppose you start at the point A, comma, f of A, and you end up at B, comma, f of B. Provided that f is continuous on the closed interval a to b, and that f is differentiable on the open interval a to b, then you can eyeball it. You can see that there's got to be at least one value of c such that the slope of the tangent line is equal to the slope of the secant line. Would you please now eyeball that value of c and draw the tangent line at that value of c, so that you can get the experience of graphically locating the value of c that's guaranteed to exist according to the mean value theorem. When you're done, you can look up here, see if you located it. I found it. There it is. It's got to be right there. That's the value of c such that f prime of c, the slope of the tangent line at c, is equal to the slope of the secant line, f of b minus f of a over b minus a. Okay, so that's the basic idea behind that. So now let's go up to the box and put it into different words. That is, if f is a position function of time t, then there's got to be at least one time on the interval a to b such that the instantaneous velocity is equal to the average velocity. So if your average velocity exceeds the speed limit, then the police officers know that your instantaneous velocity did exceed the speed limit. You can't go to the judge and argue, well, yeah, I mean, my average speed was 175 miles an hour, but that doesn't prove that my actual speed was ever 175 miles an hour. According to the mean value theorem, yes, it does. All we have to do is establish that your position function was continuous and differentiable, which is reasonable to assume that it was. Let's go to page 2. Unless you have any questions, let's pause now. Any questions on page 1, the mean value theorem? All right, page 2. Hello, and there it is. Let's do an example. The directions say apply the mean value theorem and find all the values of c on the given interval such that the slope of the tangent line is equal to the slope of the secant line. Do B and C both with and without a calculator. So yeah, we got to work on our calculator skills. I hope your calculators are out ready to go, and we'll practice that there. So without a calculator, letter A, what I'm going to do is I'm going to write kind of big so that the camera can pick it up, and I'm going to select and shrink it down. You might want to just draw as small as you can, because you might have to fit a lot of stuff in here. So before we apply the mean value theorem, I'm going to distribute the x. So please distribute the x with me. X cubed minus x squared minus 2x. And then find f prime of x, take a moment now to write down the derivative of f. Okay, so those are just some little housekeeping things that we do before we begin the mean value theorem. And now that we've looked at them, I'm going to shrink it down unless there's any questions. Any questions on how we got the first derivative? Okay, so I'm going to shrink that down so I have more room to show other stuff. Next, notice that the mean value theorem, just like the intermediate value theorem, has two hypotheses. Conditional statements are in the form if hypothesis, then conclusion. This one is actually if first hypothesis is true and H2, the second hypothesis is true, then conclusion. So we're going to apply the mean value theorem in a responsible way where we document that the hypotheses have been satisfied in much of the same format, in fact, in exactly the same format that we did for the intermediate value theorem, H1, hypothesis 1. Now, in general, hypothesis 1 is that f is continuous over closed interval a comma b. So write down the hypothesis in general, but then apply it to our specific situation. The hypothesis is that f diddlemark is continuous over -1 to 1. Well, is this function continual? Of course it is. It's a polynomial function. So think about it briefly and then put a check mark to indicate, yep, I thought about it. We're done. We have continuity over the closed interval. I'm going to, I'm going to make that even smaller. And then this one, check and done. Unless you have any questions. Any questions on verifying that hypothesis 1 applies? Okay, so tiny and put it aside now. Hypothesis 2. Hypothesis 2 is that it's got to be continuous on the closed interval and differentiable. So f is differentiable on the open interval. Differentiable on the open interval a to b, which in particular means that f is differentiable on the open interval -1 to 1. Well, look at f prime. If it's differentiable, then the first derivative is defined for all values of x. And if you look at the equation of the first derivative, it also, come on, it's a quadratic function. Quadratic functions are defined for all values of x, not to mention those from -1 to 1. So we are check mark. We're good to go. Hey, the mean value theorem applies. Any questions on how to verify and think through that the two hypotheses of the mean value theorem are confirmed? Okay, so I'm going to shrink and put that away. So this is probably what it will look like when you're taking notes. Now, the conclusion. The conclusion, which I'm going to eventually squeeze down into that area, is that, whoa is right. Whew, almost cleared, yeah. At least I didn't press the X, which would have deleted the entire page, not to be undone. So, the conclusion is, and learn these math symbols, conclusion, backwards capital E, there exists at least one C such that f prime of C equals, that is the slope of the tangent line, just think Grandma's house, equals slope of the secant line f of b minus f of a over b minus a. That's in general. In particular, there exists ditto marks at least one value C such that, what's f prime of C? For f prime of C, let's put in 3c squared minus 2c minus 2. 3c squared minus 2c minus 2 equals, and so maybe it's going to be f of 1 minus f of -1 over 1 minus -1. This is how we find the value of C using that. So go ahead and try to solve that for C. Now, we are somewhat tight for time. I'll ease up on you a little bit here and basically summarize this. This is 3c squared minus 2c minus 2. When you put a 1 in for, what is it? It's 1 minus 1, so just negative 2. It becomes f of 1 is negative 2 minus 0 over 1 minus negative 1 is 2. So you're solving the equation 3c squared minus 2c minus 2 is equal to negative 1. Adding 1 to both sides gives you 3c squared minus 2c minus 1 is equal to 0. And happy day, it factors. It factors into 3c and c. What's this going to be? That's going to be minus 1 plus 1. So using the zero product property, which says that if a times b is equal to 0, then a is equal to 0 or b is equal to 0, you get two values of c. C is an element of the set, negative 1/3 and 1. Now, 1 would have been okay, actually, for the intermediate value theorem, because you're solving over a closed interval. But the mean value theorem says, therefore, there exists at least one value c on the open interval. And since 1 is not in the opened interval from negative 1 to 1, we must select red from the palette and reject 1. There is only one value of c. We're guaranteed at least 1. Sometimes we get 6. This time we got only 1. It's negative 1/3. Negative 1/3 is the only value of c guaranteed by the mean value theorem. So, let's pause here. Does anyone have any questions whatsoever on our first example of how to apply the mean value theorem and find all of the values of c guaranteed by the mean value theorem? You, go ahead.
Wait, so why did you get rid of 1 again?
It's not in the open interval. It's a boundary value. Is 1 in the interval negative 1 to 1? Where there are parentheses?
No.
Negative 1 to 1.
Oh, so
There's at least one value of c in the open interval. So, the mean value theorem says if f is continuous over the closed interval a to b and differentiable over the open interval a to b, then there exists at least one c in the open interval a to b, such that f prime of c is equal to f of b minus f of a over b minus a. So, 1's not in the open interval. So sometimes the algebra will give you numbers that are not in the open interval. You can only accept numbers that come from the algebra or the calculator that are in the open interval. Further questions on the mean value theorem? Sloppy catch. You see the Packers game yesterday? I'm sure you Bears fans were watching the Packers game, right? For me, as a Packers fan, that was sickening. I mean, I feel like the Packers still beat the Rams, even though, I mean, they didn't have that more points, but they still beat them. All right, let's keep moving. Now, come on, don't lose it here. Yee. Okay, you know what I want to do? I want to look at, letter C. I want to show you how you do this on the calculator. Let's, I'll let you try part B on the calculator. We have time, but I want to look at part C on the calculator. Now, let me see if my calculator's up yet. Oh, there we are. Okay, so on your calculator, do me a favor. Would you please go to mode and classic? I know this is hard for some of you to go out of math print. You get, you experience anxiety sometimes when you go out of math print. I'd like you to try it anyway. Go into classic mode and go to your y equals menu. Clear out anything that's in y equals if you don't mind. And type in the equation for number 5, which is 2 sine x. 2 sine x. Notice that the closed interval a to b is 5 pi over 6, 11 pi over 6. join me on the viewing window, type in 5 pi divided by 6 for x min. Type it in. And for x max, please type in 11 pi over 6. Let's put the closed interval right in there. 11 pi divided by 6. Okay. By the way, for y min, y max, I mean the sine function, come on, 2 sine x goes from -2 to 2. And even though it's really the derivative that we care about, let's go from -2 to 2 on the y-axis. That should be fine. And then let's go to the y equals menu. Oh, by the way, does anyone need more time to get your viewing window set up as such? Who needs both time and help? I know you don't need help. Okay, so now y equals 2 sine x. Now, what we're going to do, we are going to end up turning off y1. Would you please put the cursor on the equal sign and press enter to deselect it? I mean, we still want it there. We want to call it up using y1, but we want to leave it right there. So, all together here, calculator skills. It's time for calculator workshop. I want to put f prime of c here. I want to put f of b minus f of a over b minus a in y3. I want to find out where they're equal. I want to use a calculator to solve for c. Instead of having to use algebra, I want to use the calculator. So f prime of c equals f of b minus f of a over b minus a. Okay, so for f prime, that's a derivative. So hit math 8. And please call up y1 by pressing vars. Go to vars, arrow to y vars, and pick up item 1. We want to take the derivative of y1, which by the way is 2 sine x. Once you type this in once, you can actually leave it in there. All you got to do then is go back in and change y1. It'll do mean value theorem setup for any function. I want to take the derivative with respect to x, so type in comma x for all values of x. And for y3, I want to type in question, Will?
What's the first of mean y2 like the derivative?
Math 8. Math 8. Yeah, and go to vars, y vars to pick up y1. Now, here's how we're going to type in f of b minus f of a over b minus a. I'll write it on the board to show you what it will look like. Once you have it typed in, it will say y3 equals parentheses y1 of 11 pi over 6 minus y1 of 5 pi over 6, double right parentheses, divided by parentheses 11 pi over 6 minus 5 pi over 6. That's what we're going to type in for y3. Here's how we actually do the typing. Parentheses. This is calculator notation for f of b. y1 of 11 pi over 6. It's f of x notation. So go to vars, y vars 1, 1. y1 of 11 pi over 6 minus y1 of 5 pi over 6, double right parentheses, divided by 11 pi over 6 minus 5 pi over 6. That is, there's something I don't like there, and that is this parentheses right there. Delete's got to go. So, yeah, with order of operations, that'll work beautifully. I'd like all of you to type this in. If you haven't already, start doing it now. It's going to go away in about 10 seconds. So if you want it to, you can take out your phone and take a picture of it now if you're afraid that it will go away. Although, honestly, it's here also. This is basically what's on the board. Jack?
I'm confused what y2
What y2 is?
Yeah.
It's the derivative of y1.
But what's with the x and x?
there's three arguments that you need to specify a derivative. If you want to type into your calculator the derivative with respect to x of sine x evaluated at x equals pi, which by the way, the derivative of sine x is cosine x, and cosine x evaluated at x equals pi is -1. If you wanted your calculator to calculate that -1 for you, then you would have to type in n deriv of the function. You could say y1, if y1, you could just type in sine x. But if you want to not have to type it in over and over again, you could just say y1 represents sine x with respect to x. So you have to specify that. That's the first argument. What's a function? Second argument, what's the variable with respect to which we're taking the derivative of the function? And the third argument is the value at which we'll be evaluating the derivative, so comma pi. So, I mean, if you just did math 8 n derivative of sine x comma pi, it would give you a -1. It would evaluate the derivative of sine x with respect to x at pi, and the output would be -1. You can just go to your home screen and type that in, and it would give you -1 for the answer. Okay? So that's just a way of communicating with your calculator in a way that doesn't rely on math print. Now, back to the shell. Class, once you've got this typed in, then when you press graph, look at what it's doing. It's printing the derivative of sine x, which is cosine x, from phi. This is just the snippet. And look, the mean value theorem guaranteed there would be one point of intersection, and there is. I mean, there could be more. But this is the one. So let's find the value of C guaranteed by the mean value theorem. Oh, by the way, raise your hand if this is what your calculator gave you when you pressed graph. If you were in radian mode, if you're in degree mode, that won't work. But if you leave your calculator in radian mode for life, never have it in degree mode, because in case you're in a physics class and you have to find out something like, what is the sine of 31 degrees? You can type in the sine of 31 and go to the angle menu and pick up the degree symbol. Even though you're in radian mode, you can still find the sine of 31 degrees. Never allow your calculator to ever go into degree mode, friends. Leave it in radian mode for life. Okay, so anyway, calculate, intersect, first curve, enter, second curve, enter. Guess, the value of C, guaranteed by the mean value theorem, is 4.388 approximately. I'm going to bring it in right to the lesson. The lesson is right here, and it's...
Don't you have 3 y's? Shouldn't there be 3 y's?
No, because you turned off the first one.
Oh, I didn't.
Okay, yeah, I had actually given the directions on that much earlier in the lesson. Turn off this one. I don't want the graph of f. I want the graph of the derivative of f and the slope of the secant line. So that's why there's only 2 lines. Now, class, tell you what, in the moments that we have remaining, I want to make sure that you get a statement of Rolle's theorem. So, just briefly, you want to know what Rolle's theorem is? Rolle's theorem is the mean value theorem. So, just to let you know, Rolle's theorem is the same thing as the mean value theorem, but it's a special case. It's the case in which f prime of C is equal to 0. So, when there's a third condition, the third hypothesis is that f of A is equal to f of B. Okay, so there's 3 hypotheses. It's the same 2 hypotheses as the mean value theorem, but the third hypothesis is that f of A has got to be equal to f of B, which means that you end up back where you started. If you started at mile marker 50, then you have to end up at mile marker 50. Well, guess what? That means that the slope of your average speed is going to be 0, which means there's got to be at least one value C where the slope of the tangent line is 0. That's the only difference between Rolle's theorem and the mean value theorem. So thanks for coming. The homework 3.3 is due tomorrow on hot dog quiz day.